Close. I told him I was like, even though I said that.
We still have a minute. Any questions while we got a minute? We'll pass back to Thursday TLC sheets at the end of lab, at the end of class. Substitution. Substitution.
How's it looking? Yeah.
Yeah.
Heartbeat. Recessive. Cool.
Yeah.
Alright.
But that doesn't matter.
But that was the one that was like strongly going to be used.
Yeah.
Right?
Okay, guys, let's get started. Good morning. Quiz on Wednesday, everything we've covered up to now, including mass spec. Any questions about lab this week? Questions about anything? Question?
You said it was a shaken, not stirred, Mom?
Yes, shaken, not stirred. Be a substitution reaction. Okay, let's continue on with substitution. This example reaction gives inversion, because this is R, you get S only here, which would be optically active. So we made an optically active product. That's okay, because we started with an optically active product. Substitution reaction. The bromine has been replaced by the OH. It's been substituted by the OH. The bromine is thus the leaving group. Is an SN1 mechanism more or less likely for this reaction compared to the previous one? SN1 is less likely? Why is it less likely?
Because SN2 involves both, so it's going to be backside of that.
The question could be a little bit misleading. You're telling me what the mechanism is, okay? But could an SN1 occur? I'm not saying this is SN1. Is it more or less likely? It's more likely, because this is a secondary carbon. More likely to form a secondary cation. The previous one was a primary carbon. Less likely to form a primary. That's more likely. But which mechanism does the stereochemistry outcome support? It supports SN2. Why? Because SN2 involves backside attack, kicking off the leading group, a concerted substitution, and when you do that, what do you get? And if you attack backside, you're going to get inversion of stereochemistry. On the other hand, if it was SN1, that would involve a carbocation. How do you attack the carbocation? Either side. So you should get both forward and back on the product. When you attack a carbocation, you get a racemic product because you attack from either side. We didn't get a racemic product. We got inversion. Inversion comes from backside attack. Okay? More likely, but the stereochemical Evidence supports SN2, backside attack. Okay, how is inversion obtained? Well, backside attack, but let's look at it closer. Okay, let's look at it closer. Mechanistically, the hydroxide nucleophile, these electrons attack here and kick that bromine off. SN2, concerted backside attack. That's what we did on Friday and called it SN2, for those who have not looked back at what we did on Friday. Let's look at that transition state though. SN2 transition state. How do we get inversion? Why does the product end up being S? Let's redraw the starting material. I'm going to put the bromine in the plane of the board. Let me draw this, make sure it's R first. I'll do this methyl. Now we need ethyl. If I do the ethyl forward, that's going to be S. So let me put the H forward. And put the ethyl back. It should be R. Bromine, ethyl, methyl. It's S, but because the H is forward, we switch that to R. There's R. There's the starting material. Hydroxide attacks this carbon. Where's it going to attack from? From over there, from up top, from down below, or over here? Over here. Because it attacks 180 degrees opposite of the leaving group, backside. Anytime you attack an atom and kick off a leaving group, you attack backside. I sent you a handout about that 6 weeks ago. It comes in over here. Mechanistically, these electrons come in here. And we're going to kick that off. But let's do a transition state. These electrons come in here. And at the same time, what happens to these electrons? They start moving where? Onto the bromine. So this bond starts breaking. This bond starts forming, this bond starts breaking. What does that transition state look like? We have a carbon here. I'll draw in the carbon. The bond to the bromine starts breaking, and the bond to the nucleophile starts forming. It's not completely formed, and that's not completely broken. Now, what happens to the other three groups? This moves here. These move like this. These two bonds are supposed to be eclipsed in this view. This is the transition state. Sometimes you put something like this, but this is transition state. Actually also charge. We'll come back and talk. What's the charge here? What charges can we show? What's the charge of the oxygen? Partial minus. What's the charge of the bromine? What's the charge of the bromine? Well, what does the bromine end up at the end? What does it end up at the end? Minus. It goes from neutral to minus at the end. So what is it? as it's halfway to the minus? Partial minus. This starts as minus. What does it end up at the very end? The OH is neutral in the product. So what's in between minus and neutral? Partial minus. Now what's the net charge of the transition state? Two partial minuses add up to a full minus. Well, that's what we started with. The net charge of all this over here is full minus. There's a transition state. What's another name for transition state? Yeah, activated complex, yes. Okay, then what do we end up with at the end? This bond completely breaks. This bond completely forms. We can draw that. We're going to have a carbon. The OH is completely formed. This is completely broken. H. Ethyl and methyl. R. Bromine ethyl methyl is this way, but H is forward, so it's R. What is this stereochemistry of this carbon now? It is chiral. 1, ethyl 2, methyl 3. 1, 2, 3 is clockwise, but the H is forward, so this is S. Exactly what the reaction says, right? R becomes S. How does it become S? From backside attack. Now, 99.9% of the time it's going to go from R to S. But it could do this same backside attack and it'd be R, and that would blow your mind. Because we're assuming that the nucleophile is high priority just like the leading group was. But what if the nucleophile was actually not high priority and one of these became high priority? You could end up with R if somehow your nucleophile had the lowest priority, okay? That would be not, very rare, but it is possible. Okay? So typically we'll say R goes to S. Now what is constant is backside attack and inversion. You might see an example where R went to R and it says inversion happened, and then you're like, oh. Well, inversion really means that, like an umbrella. You ever seen an umbrella invert in the wind? Yeah. And what if after it inverted it was still called R? That wouldn't mean it didn't invert. Okay? Now how does it invert? First off, what's the hybridization or the, I'm sorry, geometry is the same thing. What's the geometry of this carbon here? Tetrahedral. What is it in the product? Tetrahedral. What is this bond angle here? 9.5. All those bond angles 109.5. Okay? What is geometry here, though? Now, do you consider this partial bonds? Let's ignore them. What's the geometry of the three groups here? 2, 3. Now that's supposed to be right behind that. That means you have a plane here, and it's trigonoplanar. What are the bond angles here between these two groups? These two things here are supposed to be like this. Okay? This is straight up. And then those two are supposed to be eclipsed. Okay? It's trigonoplanar. Down, boom. Okay? Straight down, boom, boom. You turn this Y this way, then these two are eclipsed. That's what they're supposed to be doing. Okay? This is trigonoplanar. 120-degree bond angles. The transition state, the groups go trigonal planar with 120-degree bond angles. Now, if you included these in your geometry, maybe you would say it's trigonal pyramidal. Take your trigonal and then put a trigonal planar. So what is the hybridization implied here? Not sp3, but, okay, it's sp3, right? Carbon's sp3 tetrahedral. sp3 tetrahedral. What's hybridization if it's trigonal planar? sp2. We can say sp2 like. Now, carbon that's sp2 has 3 sp2 hybrids. What else does that carbon have? What other type of orbital? P orbital. And the p orbital is perpendicular to that plane. There's the plane. What if we make that look like a p orbital? The carbon in the middle is trigonal planar with a p orbital, sp2 with a p orbital. This here is almost like a p orbital. It's sp2 like. Bond angles, 120 degrees. This is the backside attack SN2 transition state. It's a transition state. It's not a discrete energy well on your diagram. This is the high energy point of your curve. For this reaction to happen, you have to have enough energy to achieve the transition state. What makes it higher in energy than beginning or end, right? We start here, go here, this is A, B, I'm not going to do that. What do we do? Boom. That's B. This is A. Is there any intermediate going from A to B? It's not a discrete intermediate. It's a transition state. Okay? We know what A looks like. We know what B looks like. What does a transition state look like? I drew it for you. Why is it higher in energy than the other two? What? Let's just restate the question. Why is it more unstable? It's got what? Well, I mean, this out of charge.
Yeah, part because of bond angles.
Bond angles?
Hard.
Bond angles 120, why is that there?
Stress.
Bond angles could be bad. Indeed, the bond angles potentially could be bad, but not always. What if you had a reason where it could not go to 120? What if the bond angles could not achieve 120? And then that would be maybe even more difficult to achieve. Reasons it's higher energy, it's not as straightforward. You got partial bonds. I mean, partial bonds are not discrete bonds. Let me sort of re-ask the question. What are things that we have to be aware of that can cause the energy to be high? This group has to find its way backside. What's going to be easier? if these three things here are small or large? Small, right? The smaller these three things are, the more accessible this is from get backside. What if these three things were big, like T-butyl groups or huge alkyl groups? It could really block this area. And this getting in, when these electrons come close, this is all electrons. As electrons come close, high energy, the energy gets high. This will be important. The crowding here will be important. Also, the bond angle will be important because it has to achieve a 120-degree bond angle in the transition state. As we move forward, we'll show some examples and we'll refer back to what I just said right there. Crowding, as this approaches, on the raise the energy. Okay. I wish I could take this and put it here, but hopefully you got it on your paper. Questions about the transition state? So some consequences of this. Maybe I'll leave it up there for a minute. Look at these two reactions here. If you take this alkyl bromide, it's a ring, and this alkyl bromide, react it with potassium iodide. The iodine can replace the bromine. This is an SN2 reaction. Rate of that, if the rate of that is 1, the rate of this one here is much slower. Why is it much slower? Well, what's this bond angle here? 60. Between two of the groups there. 9th grade geometry tells us that's 60 degrees. Okay? Which is already strained. Because it's a tetrahedrocarbon, it'd rather be 1 and 9.5. Okay, this is SN2. That means the iodide is going to come in here and attack and kick off the bromine, but it goes through this transition state. The groups here, what's the bond angle between the groups in the transition state? The preferred or required preferred bond angles. 120. Is this going to be able to achieve 120? Why do you say no? Because it's stuck in a ring, which is stuck at 60. Can't achieve 120. How's this ring going to open up to 120? It can't. Or, it could do something. Now, it doesn't have to be 120. No, that's just highly preferred. Just like tetrahedral, highly prefers 1 to 9.5. But we see there's times when it's less than 1 to 9.5, right? There's also times when it's a little bit greater than 1 to 9.5. But this is not going to be able to achieve the highly preferred 120. That's more likely to achieve the highly preferred 120. Because this can't achieve it, it's much slower. Maybe it achieves, I don't know, something, and the reaction still goes, but it's just so slow because it hasn't achieved the optimal 120. So, understanding the transition state bond angles allows you to understand this rate. Questions about that? Okay, the next here. SN2, and by the way, we're going to concentrate on SN2 for a good bit. That doesn't mean that you don't know the SN1 mechanism. SN2, backside attack. These guys down here, boom, 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 are all very reactive in SN2. Those 4 or 5, whatever, are much more reactive than this. First off, what's your best leaving group? Of the halogens, which one's the best?
Iodine.
Iodine. So are these better because it has a better leaving group? No, we're dealing with the same leaving group, so you can't, okay? Why are those more reactive? And I'm glad I left this here. These are all more reactive because there's a p orbital next door to the reactive site in all of these. P orbital here, p orbital here, p orbital here, p orbital here. It's actually 2 there. They all have a p orbital immediately adjacent to the reaction site. Let's put a p orbital immediately adjacent to this reaction site here. Let's say that this has a p orbital. Now that'd have to be like a pi bond or something. Okay? It continues on. Let's put a p orbital here. Now the fact that these are faster implies what about the transition state energy? It's going to be lower. I would make it faster because if this energy was higher, it would be more difficult. So this implies that the p orbital next door makes this lower. Why? Why would the p orbital next door make this more stable? What do you have here if this, what does that look like? P orbital overlap? Is p orbital overlap a good thing? What's the general term for a lot of p orbital overlap? Conjugation or resonance? Yeah. This is like a p orbital in here. And the p orbital next door will stabilize the transition state. That's why all of these react very fast in SN2. Does this guy have a p orbital next door? No. It doesn't have that extra stabilization in the transition state. These actually are so reactive they tend to be toxic. All 4 of these are quite toxic. Because they get in your body and the nucleophiles in your body, boom, transition state, very easy to achieve. Substitution. Benzyl chloride. It'll make your eyes tear up because it starts reacting with proteins in your eyes a little bit. I mean, if you, a very small amount, enough to make them irritated. I mean, if you put benzyl chloride in your eye, you're going to be blind. Just react, okay? But a very small amount, a trace amount, will make your eyes get sensitive to tear. These are all toxic. They can cause cancer because they can alkylate your DNA. Your DNA has like amino groups, nucleophiles, and the nucleophile can come in here and kick off that chlorine because the transition state is so stabilized by the adjacent p orbital. This guy here, it's not that reactive. Relatively. It will undergo an SN2, but it's going to be more difficult, higher heat is required, longer reaction time. Indeed, that is propyl. But this right here, what's that? Ethyl chloride? Or you can call it chloroethane, 1-chloroethane, known as ethyl chloride. Anybody know what that's used for? One use? Anybody seen baseball, like when a batter fouls a foul ball off the ankle and he's like, the trainer comes out and sprays something on it? What do they spray on it? Or why? What are they doing if they spray it? Numbing, cold. Yeah. It's ethyl chloride. It's condensed, but when it comes out, it quickly turns into a gas and it makes the area cold. They also use it in dentist office sometimes to numb things. Ethyl chloride. if this was highly toxic, they wouldn't be spraying it. Well, guess what? They ain't going to come out and spray this, because if they did, they'd have to evacuate the stadium. Much more toxic. Okay? Hopefully you can understand why. Okay, you remember we talked about that crowding. If it gets crowded in the transition state, the nucleophiles are going to have a tough time getting in there. And that will thus be higher energy, because when the nucleophile comes through all this crowding, it's like high energy. I have to overcome this energy. Well, we can look at the effect of carbon substitution at the site of nucleophilic attack. Now the leaving group is all the same here. Bromine. Methyl bromide is going to be your most reactive. Primary halide next, secondary halide, a little bit slower. Tertiary halide, slowest. And indeed, you never do SN2 with a tertiary halide. Because when you try to come in here, okay, if those H's are there, it just gets too crowded. It's like, I can't get in there. Okay? It's too crowded. Now this guy has some crowding. But we know that you can do an SN2 here, and so it can sneak in here. Now it's going to be a little slower. Which one's going to be easiest? Bam. Okay? This is referred to as steric hindrance. The more steric hindrance you have around your reaction site, the carbon that's attacked, the carbon with the leaving group, the more difficult the reaction. And indeed, secondary halide is okay for SN2. That's what we did at the top of the page. In fact, those examples there are secondary. Never do SN2 with tertiary halide. Steric hindrance negatively affects the rate of SN2. I put a little exclamation point there. Hopefully get you to read that. What about SN1? Which one of those four would be best for SN1? Tertiary. Because the rate determining step in SN1 is formation of what? Carbocation. Which one's going to be the easiest to make the ionization to give carbocation? Yes. The trend is just the opposite for SN1. In fact, when we get over to SN1, we'll say only these for SN1. You typically, don't we say you don't want to make a primary carbocation? You don't want to do SN1 with that. And you certainly would not do SN1 with that. The trend is just the opposite. You really need to know your two mechanisms, rate determining steps. For example, in which mechanism, SN1 or SN2, is the leaving group involved in a rate determining step? I'll let you think about it. But that type of question you got to know. Because if you don't know that, then you're not going to be able to then answer the next question. Here's just some actual rate data. Take the carbon and the bromine and try to replace it with an iodide. Use acetone as solvent. Here's the rates. If it's methyl, it's 163. If it's primary, it's 1. So you see that the methyl is 163 times faster. Secondary, the rate starts really slowing down, but it still can be done. It's not great, but we say it can be done. Tertiary, negligible, that basically means don't do it. Okay? Trip to the dentist. Anybody familiar with dentistry anesthetics? Novocaine, lidocaine, lidocaine, things like that. Some of them are pretty short acting, like 5 to 15 minutes. So you can do a quick procedure. After the procedure, you want your patient to be able to talk, as opposed to going all day, pardon my English, okay? So you would like it to last a short time, or maybe it's got to be a long procedure. It's going to take 2 or 3 hours to do the procedure. You want it to last longer, okay? So there's different anesthetics, short-acting, long-acting. Well, the anesthetic lasts until it gets metabolized. Once it gets metabolized by the body, the effect goes away. So it's really based on how quickly they're metabolized. Well, the metabolism is governed by sterics. Now you can look at the structure and the chemistry. The chemistry is actually organic 2 chemistry. But it's governed largely by sterics. Those that have lots of steric crowding around the reaction site, are those going to be metabolized fast or slow? Yeah, they're metabolized very slowly. So do they act for a little bit, or do they act longer? They act longer. If you look at the structures, short-acting versus long-acting, the long-acting ones have a lot of steric hindrance, bulk around the reaction site. It slows down the metabolism and makes the drug last longer. Okay? You can compare lidocaine to a lidocaine. You can look them up on Wikipedia. Now again, we're not looking at the details other than just saying how steric hindrance can rear its head and be the basis for lots of things. Make the reactivity slow. Sterics is never going to speed up a reaction. Congestion is going to slow things down if molecules have to come together. Okay. Leaving groupability. And by the way, we're focusing on the substrate of the leaving group in these examples. We've already said this, but the leaving groupability of the halogens is larger halogen better. Okay, these 3 are okay. Fluorine typically not a good leaving group. Even though it's the most electronegative, and F- is like the most stable, but is it really? It's not really, because it's so small. It's also bond strength. The CF bond is your strongest bond. So if you're breaking that bond in the transition state, it's going to be difficult to do that. That implies higher energy. The CI bond is weaker. For example, look at here. If we have this alkyl iodide reacted with this, okay guys, what's a nucleophile here?
OME.
Okay, this is K plus. What's minus? O. O, CH3. Minus, okay? Over here you made K plus, I minus. Potassium didn't do anything. It's called a spectator ion. Okay? You got to learn to ignore those. Methoxide, just like KOH, if that was an H, it'd be KOH. This is methoxide. These electrons attack the carbon backside, kick off the iodine, insert it, we know the transition state, we can get this substitution product, I minus. K plus can be shown with the I minus. You try to do this with this guy, it's going to be very difficult to impossible. But there's going to be an easy substitution reaction. That's because fluorine is a bad leaving group, not a good leaving group. Again, why the CF bond is much stronger than that one?
The electrons are closer to the nucleus.
Do what?
The electrons are closer to the nucleus.
That makes the bond stronger. Makes the bond stronger. There's a couple of other reasons, but I think that's enough. Okay. More stable anion, better leaving group. I minus is more stable than F minus. That's why HI is more acidic than HF. All right. Now your halogens are your most common leaving groups. Now for me, the bromine is the best. Why? In practice. Because iodine compounds tend to be more expensive to buy. They're also less stable because they can undergo radical reactions. Bromine, cheaper, more stable, still a good leaving group. Now the cheapest, if you wanted to buy some starting materials, the chlorine would be the cheapest. The problem is it's a little slow for substitution. So bromine is sort of the best of both worlds. And so for me, I kind of like bromine the best. Iodine compounds are just a little less common. Now in industry, they're going to use the chlor because they're going to use the cheapest. But they also have tricks to make the reaction very, very good. Research scale, you probably use the bromine if you can have a choice. But can groups other than halogen be leaving groups? Yes. Let's look at some. What about oxygen? Can it be a leaving group? Well, look at this. If you take this alcohol, let's make this an OH, react it with the same nucleophile, let's get rid of that, right? Can we come in here and kick that off? If we did, it would give this product, that here, hydroxide got kicked off. Problem is, you're not going to get a reaction. That says that OH is a bad leaving group. Because it does react with iodine, good leaving group. Hydroxide will not act as a leaving group in a slow rate determining step. Which mechanism does leaving group leave in the rate determining step? SN1 or SN2? Which mechanism does the leaving group leave in the rate determining step?
SN1.
Who says SN1? Who says SN2? Who says both? You're correct, both. Everybody has looked at the mechanisms and asked these questions? Okay? You need to make sure you know. You need to digest these mechanisms, ask questions about them. Everything we're doing. The determining steps are hugely important. Why do I say in a slow rate determining step? That applies to both. That's because in organic 2 we'll see mechanisms where the nucleophile leaves not in the rate determining step but in the fast step. If the leaving group leaves in the fast step, OH will actually leave. Okay, how can we make this reaction work? We can do it. We have to do it a little bit differently though. If you take the alcohol and treat it with methanol and acid catalyst, we can get a product. And in this scenario, the OH has left. So in this scenario, the OH can be a leaving group. What's going on here? What's going on here is that the acid catalyst first reacts with the OH, and the first thing you do is an acid-base reaction. And you get this. Right? Your whole acid-base mechanism. Now, which side's favored? Well, if you think about it, actually that side's favored. You should be able to digest that and explain that. That doesn't mean we can't form a little bit of it. Now, the methanol, which is a nucleophile because it has a lone pair, will come in here and kick that off. But it's not hydroxide that's leaving. What's really leaving? Water is leaving. It's a much better leaving group. Okay? H2O is good Lg. Really, it could be more broadened out. This requires a positive oxygen, a neutral oxygen leaves. Neutral oxygen will not leave, but a positive oxygen will. So see, it wants to go back neutral, and it's like, okay, how can I come back neutral? I'll let you come in here and kick me off, and I can come off and I can get these electrons back. Now look, what does this mechanism arrow movement give? It doesn't give the product yet. We now have the O-methyl attached here, but this oxygen has an H on it. We get to that point, and we just made this bond. Plus water. Here's the water. Now, how do we go from here to final product? We have to lose the H. Well, what was the minus here? What's your favorite acid? Okay, this is a strong acid. Just like when we hydrated alkenes, what type of acid did we use?
H2SO4.
Okay, so maybe this is HSO4 minus. Gotta have a minus. Well, this minus can take the H, leave these electrons behind, we get that. What do we reform? We reform our acid. The acid was a catalyst. This becomes protonated by the sulfuric acid. Now it's a good leaving group. How did we make oxygen a better leaving group here? We protonated it. Now, this mechanism, is it SN1 or SN2 that I showed? Right side attack, kick off the leaving group at the same time, that's SN2. But really, this right here is the SN2. It's the substitution part. What did we do first here? What do you want to call this? Protonate the OH? Or we can say we activate the OH. Then we do the substitution, which is just one step. It's a one-step substitution. Then what do we do here? We deprotonate that. A lot of students see 3 steps here and say it ain't SN2. SN2 is just 1 step. Well, no, the substitution part is 1 step. We had an activation step, and then we had to remove proton. So, in the end, how do you make OH a better leaving group?
Protonated.
Protonated. With what? Strong acid, which is a catalyst. Why didn't we use KOMe here? Why didn't we just throw in some H plus here? That's shown below? No. Why not just throw in some H plus with the methoxide? I think it's on the next page. And we'll end here. Why not just take the same here and throw in H plus? These are not compatible. You can't have a base and an acid in the same reaction. Potassium methoxide is just like potassium hydroxide, a base. If you combine the base and the acid, these two are just going to react. So instead of using the anion as the nucleophile, what did we use in the reaction at work? In the reaction at work, did we use the anion? Did we use the anion, or did we use the neutral? Obviously, it's the neutral form, right? Yeah. It still can be a nucleophile. Now we'll talk that it's not strong, but you can't use the anion and the acid catalyst together. You can't have your cake and eat it too. It's like if you fill your tub up with hot and cold water and you put stir bar in it. You no longer have hot or cold after it's okay. You can't say, hey, I'm going to use the hot part, and then hey, I'm going to use the cold part. Neither exists anymore. It's now just warm. Neutralized. As long as you got a good stirring, and I'm going to assume that things are homogeneous. Okay, guys, have a good day. Question? Lab reports? Call them out on the way out. Armand? Please yell if you want it. Larisha?